This video is all about Module 4, the physical layer. The physical layer is a great layer to start, number one, because it's at the bottom of the OSI model, but number two, it's very tangible, things that we can see, things we can touch, things we can build. It's a very practical part of networking. So the purpose of the physical layer is to make that physical connection. So like it says, whether we're connecting to a printer or we're connecting to a website, whatever we're doing on a network, playing a game, streaming audio, streaming video, there has to be some sort of connection. Without a connection, we can't do anything. If you ever had, your internet go down or maybe your cell service go down, that your device really can't do much without that connection. So it's very, very important here. The physical connection can come from a wide variety of things. It can either be, um, I should say, three main options typically. That is wired connection, or Ethernet as we call wireless, like through a wireless router where we're using radio signals, or through fiber optic where we're using light pulses. Now, most of us at home probably have a wireless router. A wireless router is a unique device because it actually is like three in one. What it has is wireless antenna. So the first thing it has is wireless antenna so that we can send and receive radio signals. The second thing that it has are Ethernet switch ports. So it's an access point, a switch. In this case, it has four switch ports, and a modem. Can be a modem depending on which device you have. A modem in one, or in this case, this one doesn't have a modem. It just has an internet connection, which would connect to your internet service provider. So it does routing, it does switching, and it does wireless through the wireless antenna. And depending on the device, it could also do modem capabilities. So at the physical layer, again, we're down at the very bottom. After we've taken the large chunk of our data, maybe it's an email or web browsing traffic, and we break it down and we encapsulate it. Eventually, where we end up is in our ones and zeros. So the ones and the zeros, as we see going across the line, this is really the physical layer. How do we make that connection? What do the connectors look like? How do we interpret those bits? All of those different things. Just like we talked about in the last chapter, all of these different things have standards, and there's many different standards organizations that come up with them. I think in the last video I mentioned the wireless standard IEEE 802.11. I think I also mentioned the TIA EIA 568A and B. That's for your wired connections, and your RJ45s and how they're pinned out and those sorts of things. So I just want you guys to know that all of our standards are defined and governed by these organizations. It's not just somebody coming up with them. Some other things besides those connections that we are worried about at the physical layer is our encoding. Our encoding is how we're going to convert a stream of bits, or excuse me, a stream of data into bits. So it could be voltage where we have a drop from high to low indicating a 0, high to low indicating a 0, low to high indicating a 1, low to high indicating a 1. We determine all of that here at the physical layer. We also are worried about our signaling. Our signaling comes in a variety of different forms depending on if we're copper, fiber optic, or wireless. But essentially what we're trying to do here is we're trying to figure out what are our ones and zeros? How are we sending those ones and zeros across the line, whether it's wireless or fiber optic or what have you? Another big aspect here is bandwidth. Bandwidth is our speed. There's three different types of bandwidth I'll talk about. The first is your, well, I guess I'll start with what most things we see as bandwidth. Bandwidth is the theoretical amount of data that you can get, and that's typically measured in bits per second. So we have a lowercase b giving us bits. So there's actually 8 bits in a byte, and I'll get into that here in just a second. But we have bandwidth. That's the theoretical amount of data that I can send at any point in time. So if I take a look at the properties of my network card, The theoretical amount of data that I can send at any point in time here is 1081 million, that's what the M is, bits per second. Now that's just theoretical. What I'm actually getting is known as my throughput. Now, why would those numbers be different? Well, I could have collisions, I could have lost packets, I could have some latency and some delay. So if you're paying your internet service provider for a 100 megabit per second connection and you do a download speed and you're only getting 80, 80 would be your throughput. Theoretically, you can get 100, that's what you're paying for, but the 80 is what you're actually getting at any point in time. The last part of that, which I'm not sure if it mentions it in this section here or not, is something called good put. Oh yeah, here it is. Good put is what is important to us. Good put is the actual data. So when we're streaming music or we're downloading a video, we actually want the video. We actually want the music. But there's this stuff called overhead, like the addresses, the frame check sequence, all of that stuff that we see inside of a packet frame. I shouldn't say packet frame, a frame or a packet. That is known as the good put. So that's what we really care about, is the good put. If you want to get an idea of how fast your internet connection is, you can just do an internet speed test. And you can run your speed. I like here in Bismarck from Midco because that's our internet service provider for most. Now what this is going to do is give us an idea of what our throughput is. We're not really sending a whole bunch of significant data through the network with this, so it's just, again, really sort of a snapshot of my theoretical speeds. So for me, I am paying for 500 megabits per second. I'm only getting about 340 today. Why would that be? Well, I got several other devices in the house that are using the network, streaming probably YouTube or something with the kids. I know I have someone downstairs playing PlayStation. So that's eating up some of my bandwidth that I'm paying for. I'm also through wireless. With wireless, you never get your advertised speeds. It's just the way that it is. Only a few devices can communicate with the wireless at a time, and that slows some things down as well. One quick note I would say on that, I have never paid for the highest speeds from my internet service provider just because, in my opinion, it's not worth it. You never get those. Typically, your devices can't handle them anyways. I have a firewall. My firewall is only rated for 500 megabits per second. So if I paid for anything over that, I would just be wasting my money. So I never really listen to the salespeople, I guess, when they're trying to sell me gigabit per second connections and those sorts of things. It's not worth my money. Going back to the bits and the bytes. So there's 8 bits in 1 byte, and 1 byte is roughly equal to 1 character. So if I opened up Notepad here, so I just opened up Notepad here, and I'm going to type the letter A 3 times. This file size should be 3 bytes. Okay, I have 3 characters. I said that each byte is typically equal to 1 character. So if I save this, and I'll save it right on my desktop so I can find it. And then I take a look at the properties of it. Three bytes in size right there. So when you take a look at a file and you look at its size, you can kind of relate that maybe to, characters, for example. So if I take a look at this picture is 5.08 megabytes, 5,329,746 bytes. So in terms of letter A's, it's about 5 million letter A's. So if you're going to download that picture from a website or something, you're downloading like 5 million letter A's. So maybe that'll give you some sort of reference for the file sizes. Now, like I said, there are 8 bits in a byte. So when I take a look at your bandwidths, and I'm paying, for example, 500 megabits per second, I really need to divide that by 8. So I am paying for 62.5 bytes per second. So I can download, let's say million, so 62.5 million bytes per second. That's a little bit different than the 500 megabits. That number always looks larger because they're advertising it in bits versus bytes. And what we really care about probably is the bytes because our files are in the size of bytes, not bits. All right, the most common type of cabling and physical connection that we have is copper. Copper uses electrical pulses to send the signals. The reason why it's the most common is because it's the cheapest and easiest to work with. In a matter of 5-10 minutes in class, I can show students how to make cables, and we can make them and we can have them be used on our network. It does have some drawbacks, however. Some of the things that it's susceptible to are EMI, or electromagnetic interference, and radio frequency interference, as well as crosstalk. Now, you guys are probably too young to remember this, but when I was just a little boy, when I was watching cartoons on Saturday morning, what would happen is that was the day my mom would clean and vacuum. And whenever she would turn on the vacuum cleaner on the TV screen, I would get some interference. I would get the screen kind of being scrambled, and I'd be yelling at my mom, "Hey, turn off the vacuum! I'm trying to watch TV." That was electromagnetic interference from the motor of the vacuum. So our electrical signals are very prone to that. So if you have copper cables, you don't want to run them um, near electrical motors and boiler rooms, around fluorescent lights, those sorts of things, because they're susceptible to this. And then since the wires are so close together, they are potentially susceptible to crosstalk. So here's some examples of copper cable. We have unshielded twisted pair. Inside of the copper cable, there are 8 wires, and they're twisted into pairs. Now, the twisting of the wire helps keep the signal on the line as it's going down the cable. It also helps that signal from jumping over to another pair. The more twists you have, the higher rated that cable is going to be. It's also going to make it more expensive, however. This is very susceptible to those types of interference. Then we have shielded twisted pair. Shielded twisted pair has a foil in there and typically individually wrapped pairs of wires. This helps shield from some of those types of interference. This is going to be more expensive because there's more material in there. And then finally, we have coaxial cable. This is still used in many internet service providers because this is the foundation that they were built on. Just one conductor here. However, many of the cable providers are switching to fiber because this is limited in speeds. So the unshielded twisted pair, pretty simplistic, I guess. Again, I talked about the twists. I talked about there's no additional material in here to protect from the interference. And then we have the different color codes. So theoretically, I could take those color codes. I'm gonna skip ahead here just real quick. I could take those color codes and I can put them into any order that I wanted into my RJ45 plug. And as long as they are the same on one end of the cable as they are on the other cable, it could work. However, what we've done is we've come up with a standard, and that standard says on the left it's going to be white-green, and on the right it's going to be white-brown. Actually, the 568B standard tends to be used more often, where on the left we have white-orange, and on the right we have brown. Let me go back up to where I was. Shielded twisted pair, again, more material in here. It's protecting us from the EMI. We're going to have foil. We're going to have maybe some braiding in there, a little bit more expensive, but it's better if you need to run where there's fluorescent lighting or electrical motors, those sorts of things. I won't spend a ton of time on the coax. It's still out there, older technology. but we have different types of connectors. We typically don't see this a whole lot in networking unless you're working for an ISP, internet service provider, I mean by that. Okay, so the unshielded twisted pair, a couple more kind of statistics about this is with the unshielded twisted pair, we can go about 100 meters, so about a football length in our distance before we must hit some sort of device or repeater or switch. If we go longer than that, then we're going to start to have our signal be degraded. Now there's different categories of unshielded twisted pair. Most common right now is category 6. Category 6 can go up to 10 gigabits per second. A lot of places probably have category 5 or 5E. Category 5 can go up to a gigabit. But most new buildings now that they're cabling out typically is doing category 6. Category 7 can go 10 gigabits per second as well. And category 8 supports 40 gigabits per second. Now again, what's the difference? Typically it's how many twists that there are and the separation of the wires. A little bit more material, so it's going to be more expensive. All of our Ethernet uses RJ45 plugs. If you're familiar with how a telephone jack looks, it just kind of looks like a bigger version of that. What we need to make this work is a special tool to crimp down these pins into the cable. You might have unshielded twisted pair sockets where we're plugging that cable into a wall jack, and those wires must be pinned out with this. The Cisco curriculum used to spend actually a lot of time on the cabling. We'd get into wire lengths and wire runs and wiring through walls and those sorts of things. But they've backed away from that because actually a lot of the electricians handle that work now. If you ever have to create cables though, it's relatively easy and it's relatively inexpensive. So if you need to buy a lot of cables, it's actually much cheaper just to buy like 1,000 feet of cable on Amazon, buy a crimper and some ends, and you can make cable very inexpensive. And it's easy. Watch a couple of YouTube videos. If you're in class, we do it in class. Cheaper than buying the pre-made. But if you're going to make a cable, you can see here we have not a good crimp on here. We cut the wires a little too long. We kind of have some twisting through here, or overlap, I should say, of our wires. We're down here. We're crimping down into the sheathing. We don't have that unnecessary overlap. It's nice and neat. That's what we're looking for. Now, as I said, we could just go and make the ends whatever color combination we wanted, but instead we came up with the standard. That way it's consistent from network to network. If you have both ends the same, so one end of the cable is 568A and the other end of the cable is 568A, you have what is called a straight through cable. Straight through cables are used for unlike device connections. PC to a switch, switch to a router, switch to a server, switch to an access point. Those are unlike devices. If you have one end 568A and the other end 568B, then what you have is called a crossover cable. A crossover cable is used for unlike devices. Crossover cables are used for switch to switch, router to router, PC to PC. Those types of devices, when they're the same type of device, needs a crossover cable. What a crossover cable actually does is it crosses over the sending and receiving pins. So 1 and 3, I believe, are sending, and 2 and 6 are receiving pins. So it ends up crossing those over so they can communicate. There's an activity here with the pinouts. I always do B. So what you would do is drag these up. I believe it's a drag, or maybe it's a click. White, orange, orange. White, green. Whoop. White, green, blue. Blue, white, green. And then white, brown, and brown. You hit check, and it tells you if you get it correct or not. Okay, fiber optic. In a perfect world, where money and time is not an issue, everything would be fiber optic. Fiber optic is not susceptible to that EMI. Fiber optic can go very long distances and it can go very fast because we have the speed of light. There's two main types of fiber. There's single mode fiber and multi-mode fiber. Single mode fiber has a smaller core and it can go much further distances and much faster speeds. We have less dispersion of light because of the smaller core. With, oh, just need to flip over here. With the multi-mode fiber, we have a larger core, so more dispersion of light, so it can't go quite as far, it can't go quite as fast. However, it's better for going around bends and corners and things like that. This is typically what you would see inside of a building when you're connecting like a switch to a server, and then outside of the building, maybe where you are connecting, oh, I don't know, a city to a city or a building to building, you typically have the single mode fiber. So since it's more expensive and is more delicate and harder to work with, we typically see it in certain situations, mainly in long haul networks. Again, maybe Bismarck to Mandan, big long connections, or submarine cables, the transoceanic cables. If you did a quick Google search for submarine cables, you could actually see where all the cables are laid out in our world's oceans to get connections all across the world, and those are fiber optic cables. Fiber optic connectors are, there's a few different types, but I'm not going to spend a lot of time on this because it actually requires special tools and specialized training. We don't do it in class because of that. It's more expensive and it's quite the process. So if we need fiber optic cables in class, which is very rare, we just purchase them. Here's a nice comparison between unshielded twisted pair of copper and fiber optic. You can see higher speeds, higher distances, better immunity to EMI, RFI, hazards, but much more costly, much more time consuming, requires specialized training and those sorts of things. All right, last, and I would probably say most common, or what seems most common to people, is wireless, because everything we have now is wireless. Wireless is great because I don't have to run a bunch of cables. I can kind of set it and forget it. I set up a wireless router and I'm kind of done. However, it is very susceptible to interference. We have limited coverage areas. Since the signal can be picked up by anyone, we have a security issue, and we do have a shared medium. Only a few devices can communicate with that access point at a time, and so we have contention for that medium. We're going to have slower connections. We're never going to have the speeds. We're never going to have the security of a wired connection. If you ever have the option of wired versus wireless, always go wired. It's going to be rock solid connection. It's going to be dedicated bandwidth. You're not going to have any of these issues listed above. There's many different types of wireless. There's Wi-Fi, Bluetooth, WiMAX, Zigbee. There is cell service. This class is mainly going to focus on Wi-Fi because that's what we see in our enterprise and home networks. In order to make a wireless network work, we need an access point and we need a wireless network card. Now remember, with your wireless home routers, as many people call them, it's actually a wireless access point with a built-in router and a built-in switch. So it's the access point mechanism of that device that's allowing that wireless connection. All right, there is more to come with wireless in different chapters. So this is just kind of a real quick overview of how it looks and how it works. More details in terms of speeds and distances and those sorts of things are to come. That is all for this video. Thanks for watching.